Alrighty. So, some logistics. Our reading discussions on FSTEM are due on Feb 12th, plus minus a day, fine. Just engage in a discourse, say something you found interesting or thought-provoking or some suggestions for the teams. Anything like that is great. I should update this. I haven't yet sent the emails because Feb 17th I learned is a holiday. And so please let me correct this. This is going to be on Wednesday, Feb 19th. So we'll have our seated discussions on Wednesday, Feb 19th. I'll send out the emails on to the teams tonight, but we should be similar format. Anything that anyone would like change? So one thing was mentioned was a little bit of background on the papers that I can give at the start, maybe like a 5 minute on each paper. Anything else that you guys think we should change for round 2? Any suggestions? Should we scrap it? Was it useless? What are thoughts? Oh, thoughts? Yeah, I'm interested. I thought it was interesting. Okay, solid. Any suggestions on what we should maybe change besides the little overview at the start, which I can provide? Nothing else? Perfect. I think all of those are fine, because in some ways research is like that. Like there's some papers that stay pretty high level and some papers that are very mathy, and I think I kind of want to show the gamut of how research works. So I think that's actually great. The more details, the better usually, but I think all the presentations are excellent. Okay, let's keep going with our little quiz. What does the I term in PID help with? Oscillations, speed, steady state error, none of the above. Yeah, they're complimented. All everywhere. Oh no.
During the school day is crazy.
Okay, fine. Yeah, because I see a bunch of folks on there already. Huh? Yeah. Give it like 10 more seconds. Let's keep going. So a little bit of a recap from last time, right? We talked about a bunch of different control rules. We talked about PID control, pure pursuit. We alluded to this idea of something called model predictive control, or MPC. One thing we're going to cover today, which is called the linear quadratic regulator, or LQR. And so there's lots of different ways to design this control rule that goes from, like I guess we thought of a feedback control rule as something that goes from U is equal to K of some X and E. Right? Something that takes in the current state, an error between your state and your like reference point that you're trying to get to. And we said we're going to get a control, right? And so there's going to be a planning procedure that gives me the reference point. We're then going to like design this function K, and that's going to be our feedback control rule. And each of these are just different instantiations of that feedback control. Okay. So let's do a quick recap of each of these, right? So we talked about bang control, but that's pretty boring. So let's go to PID first. So PID is the proportional integral derivatives controller. This combined is it's a combination of 3 terms. The proportional term, which is linear in the error. So you're just going to have Kp times error. So if you're to the left, you're going to go to the right, or if you're to the right, you're going to go to the left. Thinking about those directions wrong, but you go back towards your set point against your error. But different from bandpass control, you're going to be proportional to the amount of error that you had. And so that's going to bring you to the middle. Then we said if you have steady state error, for instance, you have a wind or a constant disturbance, or like, let's say, friction builds up in your system, right, which changes over time. The integral term is kind of an adaptive control term, which says that if you're not getting to the zero set point, you're going to try and increase the amount of action that you apply in order to get you back to something where the error goes to zero. And so the integral really helps you kill the steady state error. And the derivative is something that helps you put brakes on it, so it's not going super fast and oscillating. So we have P, I, and D term, and you're going to tune the weights of the Kp, Ki, and Kd. Right? And so you can kind of think of the proportional as the present, the integral as the past, and the derivative as the future. So that's PID control. We then talked about this problem of pure pursuit, right? And so the key insight behind pure pursuit is that cars go in circles when they steer. And so let's try and choose a steering angle delta so that my circle intersects with the point that I really want to get to, right? So let's say I'm going to like choose a point here. It's like, how do I choose my steering angle so that the circle kind of, goes through it? That's a terrible circle. It's like, you get where I'm going. Okay. So the point is we want to choose a delta and we want to use our knowledge of geometry to figure out how to go through the circle. And then we're going to take a step and then recompute, right? So it's kind of like chasing a carrot on a stick. You set a target a little bit ahead of you. You choose the steering angle to go through that target, and then you reset your target to be further ahead, right? And so that's why it's pursuing a target. But the nice thing about pure pursuit as opposed to PID, which doesn't use the model at all, is that pure pursuit is using the model in the physics of the car, right? So it's really dependent on the particular model, which is good because it's using the domain knowledge that we have. Okay, so the general scheme behind pure pursuit is you find the look ahead, you compute the arc, then you take a step along the arc, then you re-select your reference point, you recompute the size of your arc, and you move again and you repeat, right? So you're doing this replanning procedure where you're constantly chasing your tail a little bit, or chasing, not your tail, but like a point in the future. Okay, so just to recap what we did with pure pursuit, we started with these equations of motion, right? And we said that from these equations of motion with a little bit of geometry, this thing was delta. So we saw tangent delta was L over R, right? We know L, we just didn't know what R was, right? And so to get delta, we're just going to write it as tangent inverse L over R. We know L, we want to figure out what the R is going to be, right? And so we're going to express R in terms of known quantities, X, Y, theta, X ref, Y ref, which is your target point. Okay? And so our goal was to say that delta is equal to, our steering angle delta is equal to tangent inverse of L over R. We're going to try and express R in terms of X, Y, theta, and X ref, Y ref, right? And then once we do that, we have our steering angle directly. That's your control, right? And so in this particular version of pure pursuit, we're not going to change the velocity at all. Velocity is constant. You're just going to change the steering angle. And so what we did next was we said we're going to compute the arc radius. We're going to express it in terms of these two entities, A and B. You can think of it as like there's like a right angle triangle that you can form where one side is A, the other side is B, right? And we said that oh, Jesus Christ. We said that tangent delta was equal to L over R. And then we said something about R in terms of these two things, A plus B. We said it is A square plus B square over 2B. Right? And then we want to express A and B in terms of X ref, Y ref, X, Y, and theta. Right? So basically, the steps to get here are you really want to compute delta. You write tangent delta as L over R. You write R in terms of A and B. And you write A and B in terms of X ref, Y ref, X, Y, and theta. Right? So 3 steps together. Okay, so typeset, we did a little bit of Pythagoras theorem here, and we showed that RPP is A squared plus B squared over 2B. And then we then said that like to get the A and B, you kind of rotate the frame of reference. Right. So you can take this particular thing, you think about rotating by minus theta so that it's like aligned so that this thing is facing upwards, right? And then you can compute A and B as the difference between x ref, y ref, and x and y. And the r of minus theta is to rotate into the right frame of reference, right? And so to get A and B, you take difference between x ref and y ref, which is in the origin frame of reference, and then you rotate it into the car's frame of reference to get A and B, right? And so that's exactly what you'll do in your homework. There'll be a function to rotate into frame of reference. And then you take that, you stick in a square plus b square over 2b, and that's it. It's very easy. I know there was a team who said there was a sign error. Is that team here? I checked it, and I'm pretty sure there's no sign error. Okay, look into it. Otherwise, come chat with me. But yeah, I checked it last night, so I think it should be fine. But yeah, so that's pure pursuit. You're just gonna work out A and B. From A and B, you're gonna get RPP, and then you're gonna get delta is equal to tangent inverse L over R. That's it. Right? And so that's going to be your delta that you're going to use for your controller. And you just keep choosing a new point and repeating this. Now, in pure pursuit, you only have one thing that you can really choose, which is the like distance that you look ahead, right? So what we said is that, hey, from this point, we're going to choose a look ahead distance on the path, right? And so the distance we're going to, or like, let's say a car was here, you're going to choose some look ahead distance on your path. And your choice of look ahead is going to determine how tight your pure pursuit controller is, right? And so let's think about the two cases, right? One where L is really small. And so what's going to happen when L is really small?
Like really trace over.
Right. It's going to go really, it's really going to trace over the line. And so it's going to be really sharp and kind of oscillating a lot, right? And so basically you can kind of think of it as like, it doesn't let you ever like smooth out your paths. It's going to like go right to the next thing. And so if it's like off here, instead of like going to this point, it is going to try and go back to this point, right? So it's going to take really sharp turns and it might end up with like kind of a wavy path like that. And if you choose L to be too large, what happens then?
Like in the extreme case, it's always
You just go stretch it. Exactly. So you tend to like have smoother paths, but if you have smoother paths, sometimes you miss important parts of your path, right? And so you might say that, hey, your planning actually chose this path to avoid a pillar, but if you like just choose this point right here, you're like, meh, and dead, right? And so you want to be careful about, it's often a hyperparameter that you'll tune. But there's kind of a trade-off between something that's really sharp and kind of dirty and smooth, but missing important parts of the path. Okay. Any questions about pure pursuit? Yeah.
I'll also be like dynamic, because I know like this thing talking about like editing parameters for sampling, right?
It could totally be dynamic, yeah. So like perhaps in like free space, you want to set L to be large and then tight corners, you want to set L to be small. Yeah. You like to do that in your homework. That'd be great. As in, it's not obvious when to choose which, but if you can, that would be excellent. Good one. Okay, so the general design decisions for such a controller, you get a reference path. You then pick a reference state. So the reference path will come from something like planning. So a planning procedure will give you a path. Then you pick a reference state, you compute the error, and then you compute the control law. We talked about a few different ways to do this. The first one was bang bang control, right? So we did these three things, and now we're just trying to figure out this guy. We started with bang bang control, then we went to PID, then we went to pure pursuit. And so the nice thing about bang bang control and PID control is that they're super generic. You can apply them across any system you want, right? And pure pursuit is super specific. You can only apply it to cars which move in these kinds of circles. But they're on like two ends of the spectrum. So these guys are super generic to apply to any system. These guys are very specific. But you kind of want something that lies in between, right, for different types of systems. Okay, and so that's how we go from pure pursuit to optimal control and LQR and so on. Any questions before we move to LQR? So the idea behind LQR is to kind of find an in-between between things like bang-bang control and PID control, which are model agnostic, and something like pure pursuit, which is really specific to cars moving in circles. Yeah. Okay, so the nice part about these two are that they're model agnostic. The nice part about pure pursuit is that it's super simple, right? And you can just do some trigonometry to get there. But they're not always applicable to every system, right? The other thing is that it's not clear that they're optimizing a cost function. Right? So sometimes you want to get somewhere, you want to do a shortest path, you want to avoid obstacles, you want to conserve fuel, you want to avoid sharp turns, right? And so the idea of optimal control more generally is that you don't want to just get to places, you want to get to places while optimizing costs, right? And so idea behind RL and optimal control and all of these things is that you're not just trying to like get to a point, you're trying to get to a point while minimizing a cost or maximizing a reward. And so what optimal control is going to do is going to go beyond these paradigms to something that optimizes a cost function, right? And so the idea of optimal control, the reason it's called optimal control is because it's recasting control as an optimization problem, right? So optimization problems are maximization or minimization problems typically, which you're trying to say that you're trying to find the choice of your parameters so that you maximize or minimize some value, right? So like you can think of like, any function and you're trying to find the optimum of it, right? As an optimization problem, you're trying to minimize costs. So you're trying to like assign people to classes so that you have minimum overlap. All of these are optimization problems. And so optimal control is trying to use that framework of optimization and stick it into control. Like so far, we have not used any optimization. We've done PID control, which are these like heuristic rules. And we've done pure pursuit, which is specifically based on a car, but we haven't really considered it to be an optimization problem, right? And so the idea of optimal control is that you're going to try and find each control actions, and you're going to try and use a model to evaluate what's going to happen in the future. And so you're going to start here. You're going to say, I'm going to like execute these actions. These actions are going to go somewhere. These are the states that it'll get to in the future, right? And you want to find the series of actions that minimize the cost or minimize the cumulative cost, right? And so the reason it's called optimal control is because you're trying to like solve an optimization problem, which kind of looks like, you do have it on my slide, yeah. Kind of looks something like this. You're trying to say, you want to find the series of controls you want to do such that when you move forward through your system with your dynamics, let's call it F, you're going to minimize the sum of costs, right? So this is going to be your like, if you remember the motion model that we had from earlier, right? Kind of the same thing. You often call it dynamics, right? It's just telling you how your system is going to move forward in time, given some state and some control. And you're saying that you want to find the series of controls such that when you start from some state and execute those series of controls one after the other in your environment, you're going to minimize your sum of costs, right? Sometimes these can be discounted. You might have a gamma to the t, right? But it doesn't need to be. And so this is called a finite horizon optimal control problem because you're saying that you want to minimize the cost over t time steps, right? But the reason it's different from reinforcement learning is that you assume that you know F, right? So in reinforcement learning, you assume you don't know F. You assume that you can just take samples from F. You can just like interact with the word. In optimal control, you know F. Like someone gives you the model and you're trying to plan through the model. Okay. It doesn't have to be so. So the other thing, if you notice this particular problem, it's finding a series of actions starting from a particular state, say like X1, that you're trying to say, what is a series of actions U1 to UT that'll minimize cost? And this is what you'd call open loop. In the sense you just like, what you're trying to learn is just, what we're trying to get is a series of controls, U1 to T. You can also learn a control rule. So you can also learn, instead of a series of actions, you can try to learn a control rule, let's call it K, such that UT is equal to K, XT, ET, something like that, right? And so, or maybe not even ET, but you could just say like UT is equal to K, XT, right? And you could try to find a control rule. And so optimal control problems are often a mix of like, some people would solve like getting a series of actions, some people would solve getting a control rule. Yeah, that's a great question. So, if you're in the infinite horizon setting, like say you're here, right? Then you typically will have like one control rule because it's for infinite. You can't be time dependent. If you're in the finite horizon setting, you typically want to be um, time dependent because what you may do with one time step remaining might look very different from what you do with 10 time steps. So in the finite horizon, you typically will try to say you write as k sub t, and in the infinite horizon, you write it as like k. Yeah. Okay. So that is the general problem of optimal control. So the cost can be things like smoothness, preferences, if you want to go this path or that path. Action cost, like you really want to avoid, spilling things if your robot is moving, like all of those would be costs. You really want to avoid collision. Those could all be costs. Your dynamics model F tells you how the world works, right? But it could also include things like velocity or acceleration bounds. Like you don't want to go faster than this speed. You really don't want to like veer your drone upside down, right? Like in the general optimal control problem, all of that would be constraints, and you're trying to minimize your cost subject to certain constraints. Yeah. Okay. So this seems pretty straightforward, right? We have optimization problem. We have some constraints. There's one constraint, which is the dynamics. You can have other constraints. Like what makes it hard to solve? Like we've studied how to do optimization problems for 50, no, not 50, hundreds of years, right? So like why is this a hard problem? Or why might it be? What are hypotheses? Yeah. Great point. So your model might not be completely accurate. On top of not being completely accurate, it's probably not convex. And so we know a lot about convex optimization. We don't know that much about non-convex optimization. So this might be non-convex. The other thing that might happen is that you might have a huge number of constraints, and that becomes really hard to solve. And so generally this forms this like hard non-convex optimization problem. And so we're going to try and simplify it, right? As we do always, we give up on the hard problems and we make them easy. So the idea behind LQR, or the linear quadratic regulator, is basically the same idea as we did in Kalman filtering. It is saying that we don't know how to solve the general problem. Let's just solve the problem that is linear and quadratic. Okay, so what I mean by linear and quadratic is that your system has linear dynamics. T plus 1 is AXT plus BUT, right? And it has quadratic cost, which means that like you have your cost, which is a state dependent term and an action dependent term, right? And so both of them are quadratic, and your dynamics are linear and your cost is quadratic. That's why it's called linear quadratic regulator, right? And so we're going to show that if the dynamics are linear and the cost is quadratic, we can solve this in closed form. It's not generally true that you can do this in closed form. It's going to be easy if it's linear and quadratic, right? It's easy to visualize. It gives us a lot of intuition. And it's often useful in lots of real problems with some problem. And so if you want to think about this from a dimensionality standpoint, let's say your state was n-dimensional, right? Your A matrix is going to be n by n. Your B matrix is going to be n by m if your actions are m-dimensional, right? So this is the same thing we did for our motion model, if you remember from Kalman filtering. It's just the same A and same B. Yeah, for now, we'll assume that it's deterministic. We can also add noise to it. And if you add noise to it, then it becomes a LQG problem, linear quadratic Gaussian problem. Yeah. You can do linear things too, but you can also do quadratic. The quadratic is more expressive than linear. And so,
I guess then why do you have linear quadratic? Can we have quadratic for both? Why is that?
oh, because when we work out the closed form, it doesn't come to a nice closed form if it's quadratic. Good question. Okay, so in general, we're going to have linear dynamics and quadratic costs. So let's start by thinking about a really simple system, right? So we're going to have this inverted pendulum, right? The goal of the inverted pendulum is that you have a mass on some sort of stick. You can control the base of the stick, so you can apply forces here, right? You can apply torques. You have a motor there, and you're trying to apply the torques so that your thing always goes your mass always stays upright. From any starting position, you're trying to swing it up and stay upright. And so this is like a classic control problem. And so we go back to a bit of physics. The system is going to look something like this. You're going to have gravity, which is mg, going downwards. And you're going to have this torque that your system can apply externally, which is going to be tau. And those are the two forces acting on your system, right? We're going to assume no friction for now. And it's at let's say it's at some angle theta, right, to the vertical. Your goal is to stabilize it at theta equal to 0. Right? So you really want your system to go to theta equal to 0. We'll show that we can cast this as an LQR problem, and then we'll try to solve it, or approximately LQR. So if you just work out, the free body diagram here, you can see that there's mg going this way. And so perpendicular force is going to be mg sine theta applied at a tangent arm of distance L, right? So you're going to have a torque of mgl sine theta, and you're going to have an external torque of tau, right? So you're going to have mgl sine theta plus tau is equal to the moment of inertia times the angular acceleration, right? So you can show that mgl sine theta plus tau is equal to ml squared theta double dot. Theta double dot is the second derivative of theta with respect to time, right? So it's right? So theta double dot is the second derivative of theta with respect to time. You can show that mgl sine theta plus tau is equal to ml squared theta double dot. Right, so that's just from basic physics. You divide both sides by ml squared. And so if you divide both sides by ml squared, and you just flip the sides, you see theta double dot is equal to g over L sine theta. And so if you look at mgl divided by ml squared, right? G over L sine theta plus tau divided by ml squared. Right? Just divide both sides by ml squared. And the approximation that we're going to make to make this all linear is saying that we're going to approximate sine theta by the first term in its Taylor expansion. And so if you look at the Taylor expansion of sine theta, it is theta plus some stuff, plus some stuff, plus some stuff. When theta is small, sine theta is approximately theta. Right? And so what we're going to do here is we're going to approximate sine theta by theta. That's going to allow us to approximate it as a linear system. But in general, what you can think of this as is you're just applying a Taylor approximation to this. And so most systems are nonlinear, but to make them linear, you just apply a Taylor approximation, and you keep redoing that. Okay, so we've said that now equations of motion for us are theta double dot is equal to g over L theta plus tau over ml squared, right? And so what we're going to do to make this a linear system is we're going to define the state of the system as theta and theta dot. So theta is your angle, theta dot is your angular velocity, right? And we're gonna try and write theta and theta dot at t plus 1 as some a times theta dot at t plus some b times some control u, right? And so we're going to try and work out what a and b are so that it becomes a linear system. Yes. So all we did is we wrote out some free body diagram physics. We divided by ml squared. We approximated sine theta by theta. And now we're going to write this as a linear system so we can work with it. Okay. So how are we going to write it as a linear system? Something like this, right? So there's a lot of symbols. Let's try to unpack it. So let's look at the first row, right? So it says that theta t plus 1 is equal to this times this plus this times this, okay, which is going to be theta t plus delta t times theta t dot plus 0 times tau over ml squared, right? And so the first row of this matrix, whatever, equality, says that theta t plus 1 is equal to theta t plus delta t times theta t dot, right? Which is just like Euler integration. It's basic like, what do you call it? Numerical integration of derivatives. It's just saying that if you know the derivative, you can like derivative is approximately theta t dot is approximately theta t plus 1 minus theta t divided by delta t, right? That's kind of your derivative. You move things over. And so you can approximate theta t plus 1 as theta t plus delta t times theta t dot, right? That's our first row. And our second row is just going to be the same thing for theta t plus 1 dot. So we know that theta t plus 1 dot is equal to theta t plus 1 or theta, that's equal to theta t dot plus delta t times theta t double dot. The derivative of theta t dot is theta t double dot, as it means the second derivative of theta. And so you can show that theta t plus 1 dot is theta t dot plus delta t times theta t double dot. Yeah. And so now if you expand this, you can write this as theta t plus 1 dot is equal to theta t dot plus delta t times g over L theta plus tau over ml squared, right? That makes sense? I just substituted this guy into like this equation, right? And so now if you like compare this thingy and this thingy, this bottom row, they're like exactly the same. So you can show that theta t plus 1 dot is equal to g over L delta t times theta t plus theta t dot plus delta t times tau over ml squared. Okay. So expansion doesn't matter too much, but let's just think about it from like, this is a linear system, right? So the system is linear. This is your A matrix. This is your B matrix. This is your state. This is your control, right? So it makes sense because your control is just like how much torque you apply. And your state is theta t dot, right? And this evolves linearly with the approximation that sine theta is theta. Approximate. Okay. So this is a linear system, right? Yeah. Yes, exactly. So you have to re-linearize it around your curve. Yeah. It doesn't really matter. You can like absorb it into here if you want. You just like scale it. Okay. So that's our linear system. Once we define that's the dynamics of our linear system, right? Now we have to define the cost. Our cost is going to have two parts. The first is a quadratic state cost, and second is the quadratic control cost. And so remember, the costs are scalars, but this is going to be a 1 over n. This is going to be n over n. This is going to be n over 1. So this cancels, this is going to be a scalar. That same thing, this is going to be a scalar. And so we need to figure out what is Q and what is R, right? So in most cases, like someone is going to give you the cost. Someone is going to give you what Q and R are. There's like a whole field of figuring out what Q and R are. It's called inverse optimal control. But like for our cases, we're just going to think about Q and R being given. Okay, so let's try to intuit what this means though. When we think about a state cost, we're going to think about it as some quadratic x times q times x, right? And q is going to be something we call positive semi-definite. And so the conditions for positive semi-definite are down here. Or it's actually, yeah, positive definite. Or positive semi-definite, which is saying that like, it's kind of like the matrix version of positive. So it's saying that Q is such that for any z that is not equal to 0, z transpose qz is positive. And so it's saying that like no matter what z you stick in, z transpose qz is always going to be positive. or which means that X transpose QX is always going to be positive, and it's only 0 at X equal to 0. Right? And so this kind of suggests that your cost is like a quadratic bowl around like 0. And that's the point you want to stabilize at. Right? So if you wanted to stabilize at a different point, you might have your cost as like X minus X ref, something like that. Right? And so then this would only be 0 when X is equal to X ref. Right? And so you can kind of think of your cost as like a quadratic thing that kind of is a bowl which ends at the point that you care about, right? Which is 0 in this case. And so this is just an expansion of that quadratic cost. But more generally, it's just telling you how much to weight, for instance, cost on theta versus cost on theta dot, right? So really, when you want this thing to be stationary, you want theta to be 0, you want theta dot to be 0, you want everything to be 0, because you want to be at rest at the top. But you can choose the different coefficients to weight those things differently, and sometimes that affects stability in different ways. Right? But it's just saying that get to 0 and stay there. The action cost, the control cost, is also quadratic. U transpose RU. R is again positive semi-definite, right? And it's saying that this is just saying that you really want your controls to be small. Right? So you want your controls to be as small as possible. And you're saying that like you're going to get penalized for applying large controls. So don't run your system willy-nilly in the real world. Have low cost. Low cost means low magnitude. Okay? So that's all that this is saying. It's just saying that you like have your cost. It's scaled by some positive number. You just don't want it to be too large, right? And this, what you do often is you trade off this cost versus the like X transpose X Q cost. And so this just tells you how much should you care about controls versus how much should you care about state. Okay, so that is a general LQR system. And sometimes what often helps in these LQR systems is these phase diagrams, which are basically plot theta and theta dot on the X and Y axis. And then you can kind of plot paths through the space, right? So they're paths through the space, which are trying to get to the origin. So you really care about getting to the origin, which is theta equal to 0, theta dot equal to 0. But starting from different places, you might have different paths to get there, right? And so you can draw it for inverted pendulum, but it often looks like a swirl which gets to the middle. Right? So the phase diagram for an inverted pendulum doesn't look like straight lines because the dynamics of your system, you can't just teleport. You often have to follow these like swirls to get there. You can kind of think of it as like a whirlpool, which is trying to get to the origin, and you're trying to see what the controls are that'll get you to the origin. Okay, so what we're going to try and do is we're going to try and solve for the, you remember the optimal control problem? The optimal control problem was this one. We're going to try and solve for the set of controls that will solve this problem when F is linear and C is quadratic. Right? And so we're going to try and optimize for like minimizing this cost subject to these constraints. And we're going to try and find all the U's. Okay, so the key idea behind LQR, the key idea behind LQR is to just use dynamic programming. And so what we're going to do is we're going to start at the back, and we're just going to do dynamic programming backwards. And so we're going to start at the last time step, and we're going to do dynamic programming all the way to the first time step. And it'll give us a nice closed form solution. And so these are often called the Riccati equations, and the Riccati equations run backwards. We're going to start from the last time step, and then we're going to try and figure out the second last, and the third last, and the fourth last, and we're going to figure out a control rule for each of those. Okay. So we're going to try and solve this problem. Right? So we're trying to, this J is often called a cost to go, or J star. We often refer to this as a cost to go. Right? It's saying that like, what is the cost of your current time step plus your current state cost plus your current action cost plus the optimal cost in the future. Right? So like dynamic programming, you're going to go work backwards. We're going to assume everything else in the future has been optimal. And you're just going to work backwards to find the solution to this problem, starting from time step t equal to capital T, right? Going backwards to t equal to 0. So the Riccati equations are just going to try and solve this objective. Try to minimize this guy. Yes. So it doesn't have to be that you reach 0, 0. It's that you may incur non-zero cost. If you were at 0, 0, you'd incur 0 cost. Let's say so what you're going to try and do is you're going to try and find the best control rule, no matter what state you're at. So it's saying that if I was at this state, I would do this thing. If I was at this state, I would do this other thing. And so if you're not at 0, 0, you're going to incur non-zero. Right? So if I was like, it's like the best that I can do at the last steps. I'm going to find the best thing I can do at the last step, and the best thing I can do at the second last step, and the best thing I can do at the third last step. Okay, so let's try to find the solution to this. So as I said, remember this is cost to go. Cost to go is the sum of the immediate cost and cost in the future, right? So xt plus 1 is connected to xt through like the dynamics of your system. And you're trying to find the controls that minimize your cost to go at every single time step, starting from the back. Okay, so if we're going to start from the back, and we set the time to go is 0, right? So which means that I have 0 time steps to go, right? I'm all the way at the end, have 0 time steps to go. So if you look at this like this cost to go thing, this term is no longer there. You have no more time steps to go. Right? So if you're at the end, you have no time steps to go, which means that you just have to minimize the immediate cost. There's no more time steps. Right? So if I was to minimize this guy, and remember that Q and R are positive semi-definite, right? Which means they're only 0, they're always positive, only 0 when U or X are 0. And you're trying to minimize this guy. What is the optimum? U will be 0. So the optimum will be, because these are positive semi-definite, this thing doesn't even depend on U, doesn't matter. This thing is minimized when U is equal to 0, right? And so the last time step, you just give up and say U is equal to 0. That's the best you could do. Right? And so the idea at the last time step is that U is going to be equal to 0. And what is our cost going to be? That's right. None of this. Just keep this guy up, right? So it's just going to be X transpose QX is going to be your cost to go at the last step. Or your cost at the last step, right? And so you're just going to have your cost being X transpose QX. And let's call this thing P naught. P naught is going to be, we're going to use this recursively, but let's call this thing P naught for now, or P0. Right? And so at the last time step, the best you can do is set U equal to 0. And you're going to incur a cost, which is X transpose P naught X. And it's quadratic. Your cost to go is quadratic. And so you can kind of think of it as like this, this like quadratic bowl. So like I was just telling Marco, it's basically if your X was 0, then your cost would be 0. But if X is not 0, then you have like a quadratic bowl around it, right? And so at the last time step, the best you can do is 0. Your cost is quadratic with X transpose P naught X, where P naught is equal to Q. Okay. Now we're going to go to the second last time step. So we said, hey, you've been optimal at the last time step. Now let's think about the second last time step. And let's solve this objective for the second last time step. And once we're done with that, we'll do the third last time step and so on. So at the second last time step, so the first time step, or the last time step, we remember we had no future cost. We just had immediate cost, right? At the second last time step, you're going to have immediate cost, and then you're going to have some future cost from the last time step, right? And so you're going to say that you're not going to just solve the immediate cost problem. You're going to solve the immediate cost problem plus the optimal cost in the future, right? And so you're going to say, I want to solve this objective with respect to U, right? So you can kind of think of it as like, this is the immediate cost at X. This is the immediate cost of an action. Once you execute U at some state X, you're going to go to the next state AX plus BU, and you're going to take the cost of that next state, right? So you can think of it as trading off your current cost and your future cost, right? Yeah. So this is going to be the U at the second last time step, assuming that the U at the last time step was optimal. So the way that the U goes in determining the state, it goes in because it determines the state, but it doesn't affect the last time steps action. Right. So this is like, if you look at this index, this is on state.
Right.
Right. So this is like determining the state. So you can think of U as determining the next state, but not the next action. Right. The last time steps action is always 0. And so you can kind of think of this as saying, you will be determining this cost, and you will be determining what state you go to next, and you want to trade those two things off. And so we're just going to try and solve this guy with respect to U, right? Okay, so you're going to solve for control at time step t minus 1, accounting for this impact on the future through the dynamics of your system. And so this is the dynamics of your system. This is the immediate cost. And so these are the two things you kind of need to trade off. Yeah. Okay, so we're going to do a little more calculus. So we're going to say, let's take the gradient of this thing with respect to U, set it to 0. Okay, so can someone walk me through what would the gradient of this thing look like? So take the gradient of this whole thing with respect to U. And remember, okay, so first thing we want to do is we probably want to substitute what J naught was, right? So if you remember J naught, it was X transpose P naught X, right? But now our X is going to be substituted by AX plus BU, right? So it's going to be AX plus BU transpose P naught AX plus BU, right? And then we're going to have X transpose QX plus U transpose RU plus this thing, right? So we're going to try and minimize this guy with respect to, sorry, give us 1 more minute. If you want to learn about LQR, pretty cool. Take the gradient with respect to U, right? And so I'm going to go through it again at the start of next class because we're out of time. But this term doesn't depend on U. This term is quadratic in U. This term is also quadratic in U. And so we're going to be able to solve through it. I'm going to skip forward to what it looks like. The solution looks something like this. And it's going to look real nasty, but it's not actually that nasty. It's less nasty than you think. It's actually just linear. What we'll do is we'll call this thing K, and then it'll become beautiful. And then it's going to be U is equal to minus KX. Excellent. We'll go through it again on Wednesday. But yeah, see you then.
Thank you.
All right. Thanks, guys. You learn about LQR?
Thanks.